Hi, in part 2 and 3, we will learn the first rule of counting. In fact, everything else following from this beginning, I would have some kind of rule of product or rule of sum hidden somewhere. And by the way, if you need a complete picture, yeah, that we do have a rule of subtraction and the rule of division. That's a slightly more advanced topic, so we will keep that for a moment. But the basic counting techniques comes from these two different rules. And the interesting thing about this is that we learn about product before we learn about the sum. Isn't that kind of weird? Because in grade school, when you are grade 1 or just start counting numbers, you learn sum first, and then you learn a product. But in this topic, in combinatorics, it is more intuitive to take a product. If I give you a problem you have no clue how to solve, like the best thing you can do is multiply them together. That should give you a better idea than adding these two numbers together. So we start from a product, right? Because product makes more sense in this case. But what are they in the first place? Like the root product is actually intuitive. I don't even have to mention that. You could kind of guess from that, and I'm sure you have some kind of like intuitive understanding of this rule. So suppose that you are here. That's you. This is where you wanna go. That's your destination. And you have to travel from this blue country. Not sure where it is, but from this blue country to the green country. But you have to stop at the orange country. There's no direct flight or direct train or anything. You have to stop in the middle before you can continue. But suppose there are three ways you can travel from the blue state, blue country to the orange country. Maybe the first way is to use to do it by road, ride a bus, and then you can take a train, and then you can do it by boat, and you can choose any of the ways you want. And once you get to the orange country, you could continue to your final destination in two different ways. Maybe now you can just walk, maybe they are close enough. Or you can take a bus. There are no other options. Then the question simply asks, okay, how many ways? How many ways you can travel? If these are the options you have. So at a glance, you see, there are three ways for the first path, and two ways for the second half, right? So it is 3 plus 2, right? So it's 5. Yeah, that's why we start from the rule of product, because this kind of problem is more intuitive. It makes more sense to multiply them. So if you don't know the rule at all, like what you have to do first is just counting everything naively. So for instance, okay, let's say if you used to start from a bus, what else can you do? You start from a bus, then you can take a bus and then walk. To your final destination. Or you can take a bus and then take another bus. And that's the first option, bus and then walk. If you had to write it down, then it's that, bus plus walk. And that's your first option. And you can take a bus and then another bus. That'll be your second option. And you have to repeat that for all the possible options or the possible choices on the left. So if you start with a train, for the second half there are still two options for you to choose. You can take a train, then walk. And you can take a train, then take a bus. You can take a train, then walk. Train, then bus. Let me abbreviate that. Let's not use the board, and let's use the ship then. So how many ways are there now? 4 ways. And lastly, we repeat with the ship. You can imagine that, if you start from the ship, then that's the 2 way for the second half. If that's what you have, and then we have ship, then walk, and then ship, then bus. So there are 2 questions to ask. First, have we gotten all the cases? Are we missing anything? My answer is hopefully not. We can kind of see because there are not that many cases, but in practice we might miss if there are too many cases to consider. So let's say there are no, we are not missing anything. Whatever you choose, it must be one of these 6 cases. Second, did we double count anything? That's another question you have to be careful about. Did we kind of use bus and bus twice somewhere in somewhere in this list? Hopefully not, right? For instance, you might say, we can no, everything is fine. So we didn't double count, so we can kind of sort of conclude that there are 6 ways in total. And again, that comes from just a naive counting. Maybe we might miss, we might make some mistakes, but it's hard to tell unless you have a fixed way to count these things. So there are 6 ways. But if you go back one step and see how did we count, how did we list all these 6 different ways to travel, and you first see that there are 3 branches here that corresponds to the number of ways for the first half. And for the first, in this case, we use the word arrangement, or you just say for the first step. Step 1, choose one of these 3 transportation methods. Then, after you get to the orange country, then you choose 2 alternate methods. Right, and if you see how these branches work, and then if you ask how many leaves at the end, how many bubbles we have there, you say that there are 3 branches in the first in the first step, and then each step gives you 2 other branches. Right, so each of the 3 gives you 2 more branches. So the answer should be 3 times 2. And that's exactly how you check whether you have gotten every single combination or not. So that's the naive way to count, and some kind of proof or justification on why this do include everything. So that's it. Right, this multiplication. And the reason why is because of this. And because if you write it in details, okay, there are 3 methods. There are 3 ways for the first step, and each of these 3 give you 2 more, so it's 3 times 2. It's like there are 3 boxes, and each box contains 2 tickets, or they contain 2 objects. So the number of objects in total is 6. So that's the idea, right? And that's the reason why we multiply. And also, by the way, this way has a name. I don't have it in slide, but this way has a name called a tree diagram. So it's a diagram, things with bubbles and arrows. It's a tree. Why is it a tree? Because it's if you look at the tree as, if you consider the leftmost part as a trunk, as a center, and then everything else seems like a branch, or in the last step there are leaves. You have to kind of imagine that a little bit. Okay, that's a tree, that's a trunk where we start. Okay, this has 3 different branches, and each branch has like 2 leaves. Kind of. That's the 3 diagrams. And that's kind of a proof why we have a rule of product. So here is how you count and how you use this rule of product. But before we move on to the definition, we have to ask when do we use this rule? Can we just use the rule of product everywhere? Of course not, because otherwise we want to have the name rule of sum if everything on earth can be applied with the rule of product. But of course there must be some kind of requirements, and the requirements is that there are two requirements. Like first, like these two steps, that's step 1, that's step 2. These two steps must be separate. Okay, so separate and in order. Okay, so you have to do step 1 first before you can do step 2. And that's one quick requirement. And second, we have to do them all. This means you cannot just stop at step 1. You cannot just say, oh, I go to the orange country and it looks nice, so I stay there, I don't move, and then I go back home. No, you have to do step 1, do them all and in order. Do both, or do all the steps in order. And 1 and then 2 and then 3 and then 4 and then 5 and so on. So there are some tiny requirements, right? Which if you can write as this kind of tree, then it should be pretty obvious of how you count and what you do here. So there's some quick requirements before you can apply the rule of product. So let's get back to the actual statement and see what they have here. So there are two rules, 2.1 and 2.2. Let's see the first one first. The first one says that for two arrangements, steps, you perform something in different steps. So if there are m ways to arrange something, and then there are n ways to arrange something else after that. No, there are two words here, right? Something else. So they are separate. You repeat the same thing, and you do this n ways after that. Then the number of ways to arrange both of those things. Notice the keyword on board is m times n. Simple, right? It's kind of simple if you have a tree diagram and list some problems first. But the way this statement looks not that friendly. But yeah, we do need to write everything out because like these three requirements are important. Yeah, they are different. You arrange one after another, and you need to do both. So that's what we have m times n. Right, and the extension, which is that, oh yeah, what if we don't have two? If there are more than two arrangements to make, maybe 3, 4, 5, 6, or whatever, and then we can simply extend the rule and say that, oh, you just multiply them all together. Right, but the requirements still must still be satisfied. They are all different. Then you do it one way after another, and you have to do all of them. So that's the basic rule of product. So let's take a look at some examples. How many? Oh yeah, I already have 2 examples there. So first, suppose a student ID is a string which consists of a letter followed by 3-digit number. For instance, S48. The question asks how many distinct IDs are there? If this is the first time you see this kind of problem, it might not make sense because, yeah, what are arrangements? Like what are ways? What are, it doesn't agree with the definition directly. Yeah, but this is where maybe this kind of top lecture is difficult because there are many ways to express the same idea. And if I change the wording a little bit, then maybe it might throw everyone's off and nobody understand that. So yeah, what we have here, is kind of like arrangement. You do 1, 2, 3, 4, 5 in several steps. But then if you take a look at this, it is as if so okay, so in this problem you are trying to generate a sequence of four letters, alphanumerics. And the first one is a character, it's a letter, and then the rest are numbers. Then the question is, what are steps and what are arrangements? And this is where we have to think about it ourselves. Okay, this is the end. Like at the end, we need this for letters, for characters. But how do we divide them into several steps, into small processes? So here in this case, usually, like almost always, if you see a string of numbers or letters or characters, like you should think of it as you should complete them in order. And so you write the first letter there, and then you think about the next one, and you write, and then you think about the next letter, and then you write down. So here, we start from the first character, and here the first character is required to be a letter. So the question is, how many letters in English alphabet are there? And hopefully we have the same number, which is 26. And there are 26 ways to put a letter in the first character. So that's one way to make a mark. Right? But if you have to draw the tree diagram, you would get something like this one when you list them all the way to C, like from start. So that will be the tree diagram. But if you are familiar with that already, then you can use this to abbreviate all the cases. Okay, what's next? Next we have to follow that letter by 3-digit number. So there are three distinct positions to put numbers. What do we do next? Here there are no author requirement, so we can just put a digit as a second character. How many ways you can put a digit? 10 digits. So it's 0, 1, 2, 3, and so on, all the way to 9. You can put any of these 10 digits following the letter A. You can also put any of these 10 digits following the letter B and C and D and so on. So that's gonna be messy real quick, and that's why you don't want to list all the cases every time. Okay, what's next? Another digit, right? And there's no requirements, so you can put anything you want. So following the first digit, you can put 0, 1 all the way up to 9. Following the second digit, you can put 0, 1 all the way up to 9, and so on and so forth. And so this is getting messy real quick. But yeah, there are 10 of each one. And lastly, that's the last digit. Again, there's no requirement or restriction, so you can put any of the 10 digits in the last as the last character in this ID. And so on. And so by the rule of product, you have to maybe go back a little bit and see if that satisfies the rule, right? So first we have 4 arrangements. We do things in 4 steps. Right, second, these 4 steps don't interrupt each other. Right, they are just 4 separate characters in this string. And lastly, we have to do them all. Like we cannot just say, oh, let's have SFS and then 4 and then 1 and then just stop. No, you can't do that. You have to put something as the last digit. So you have to complete all 4 steps. And that's why these satisfy the rule of product. And here, since it satisfies the rule of product, then the number of ways that you can make all these arrangements, the number of ways you can generate these 4 character ID is this product, which is 26,000. there are 26,000 ways to generate an ID of this form, which also means that there are 26,000 different IDs. On Earth, or on this campus, which is not a lot. Like if there are like 4 or 5 years of students, then you would run out of ID pretty soon. But yeah, that's the concept of this one. Oh, and just for the illustration, if you are looking for the ID S418, that means you have to go to the branch where there's a letter S, and then you go to the branch where there's a letter 4, and there's some branch among that has a letter 1, and a branch that has letter 8. A number 8. If you follow this single branch, you would get to the leaf with S418 with that ID. And if you have enough spaces, you can list all the leaves, list all the possible IDs. So that's the first example. So it's about the tree diagram, about how you make your own node, and how you would interpret a single result of these arrangements or of this product. So that's one. So next we have another one. So let's see how many different 4-of-a-kind kinds are there in standard 5-card poker. It's kind of let's say a big gap between these two problems, because the first one doesn't require anything at all. The second one, though, does require you to know some poker, right, and have some good understanding of this process. So let's go back a little bit and talk about poker, because we do need that for other problems as well. So poker is played by using the standard deck of cards, and this standard deck of cards consists of 52 cards, and the cards have value as 2, 3, and so on, up to 10, and then J, Q, K, Jack, King, Jack, Queen, King, and each card has there are 4 copies of each card. They all have a suit, which could be a spade, a heart, a diamond, or a club. So those are the cards. I should rewrite that. There's a jack, a queen, and a king. So these are the cards, right? And the question asks how you can get a hand. Oh yeah, and the 5-card pokers. A hand in 5-card pokers are just 5 cards. There are 5 cards in your hand. Those cards could be anything from a deck, as long as they are not duplicate. You have a copy of Ace of Hearts. You have Queen of Diamond, Jack of Club, with Jack of Diamond, and then 3 of Heart. Those kind of combination. And the question asks how many hands you can make that has this property. And the property is that it is a 4-of-a-kind. So 4-of-a-kind means you get all 4 cards of a single face. But then if you pick a 3, then that means you get all the 3s in the deck. So that means one of them is a spade, one of them must be a heart, one of them must be a diamond, and one of them must be a club. And that's a 4-of-a-kind. And since there must be 5 cards in your hand, then the last card can be anything you want. So this collection would be considered 4-of-a-kind. The question is how many 4-of-a-kind hands are there that you can form. Which again, if you compare that to the first question, this seems different. But it doesn't seem like you can use the proof of product purely. It seems like you need to know some kind of shenanigans, some formulas, combination, permutation. But yeah, in fact, this only requires you some poker knowledge and the raw product. So before we can apply the row product, we have to divide the task into two smaller tasks. Right, what do you do first, and then what? And what kind of steps you can perform before you can get 4 of a kind, get the result you want 4 of a kind. Let me move a little bit. 4 of a kind. So if you take a look at this hand, like this hand has two kind of cards, 4 of a kind. This hand has 5 cards, and then there are 2 sets you can see. So the first set is a face with all the suits, and then the remaining card, the 5th card. Right, so that means you're gonna have to, try to pick or select in these 2 groups. So you can see, we can see that, maybe we could start from, 5 D4 of a kind cards. And this could be the first step. If you take a look, if you review the deck and look at all the cards and try to pick the cards to make a 4 of a kind. Now you could start from, okay, let's pick a number and take all the cards. The question is how many ways you can pick, how many ways you can get 4 cards where they are all the same value. And so they are 4 cards. 4 cards, same face. And also it needs to be all suits. So diamond, spade, heart, spade, diamond, and club. Now, how many ways you can get 4 cards of that property? Then you have to think about it a little bit, like, if you want 4 cards, then what are the options? If you pick an 8, for instance. So let's go back to the tree diagram for a bit. If you pick an 8, right, then that means how many ways you have to pick them. So if it's an 8, you have to pick all the 4 aces. If you want those 4 cards to be an 8, you have to pick all 4 aces. Ace of heart, ace of spade, ace of diamond, and ace of club. So there's only one way to pick 4 aces. So that's the first way. Then what about 2? If you don't pick an ace, you could pick 2. How many ways are there? Just 1. Again, because you are forced to pick all 4 cards. So once you need a 2, then you have to find all the 2s on the table. So there's only one way to achieve that. And you can see that since by the symmetry of the cards, no matter which face value you pick, then each of them have 4 copies of the same value of the same face. And that means you can pick any face you want. But once you pick that, then you have to get all 4 cards. So that's the first step. And if you ask how many ways you can pick 4 cards, then the answer is 13. So this is equivalent to just pick a face. Pick your favorite face. Do you want a 5? You want jacks? You want 2s? And then choose them all. Okay, we get a start. Okay, so we need 5 cards. Like we pick 4 already in the first steps. Then what do we do afterward? For instance, if you pick an 8, or if you pick 4 aces, like what's the next step you have to perform? You have to arrange. So imagine that all the aces are gone. Then what about the last card? This is where you pick the 5th card. Like which card can you pick? In fact, you can pick anything you want. Right, because this definition of 4 of a kind only cares about the 4 cards that have the same face. It doesn't care about the 5th card. So that means you pick the 5th card. You can pick the 5th card from It can be any card, any author cards. Notice the word author. It's not any cards. Why do I use the word author cards? Because if you pick 4 aces, then you cannot pick the 5th ace. There are only 4 copies of an ace in the deck. Unless you cheat or do some weird trick, you can have 5 aces. But yeah, there's no ace anymore in the card in the deck. So you can pick any other cards. How many ways you can pick a card that are not an ace? And you have to go back to some card knowledge. There are 52 cards in a deck, and 4 of them have been picked to be the 4 of a kind already. So there are 48 cards left that you can pick as the 5th card. So for instance, if those 4 of a kinds are aces, like then the final card could be 2 of a heart, 2 of diamond, 2 of a club, 2 of spades, 3 of heart, 3 of diamond, 3 of spade, 3 of club, and so on and so forth. And there's no restriction on what the final card or what the 5th card could be, as long as it's not one of the 4 cards. Okay, so out of 48 remaining cards, you can pick any card. And that means there are 48 ways you can pick the final card. and that's for S. And also interestingly, like, suppose you pick 2 to be 4 of a kind, and then you ask, okay, what are the 5th card that I can pick? Then if your 4 of a kind contains 2s, then you can still pick 8s as your last card to complete the hand. 8 of a spade, 8 of club, and then you have to pick a 3 because 2 have already been chosen. So there are lots of ways you can pick. But one thing to know is that these two sets are different. Because if you go back and to the 2 previous examples, like the leaves look the same for each branch. Like we have walk plus, we have 0 to 9, 0 to 9, 0 to 9. The leaves are the same for the previous cases. But here the leaves are different. It's like for the first branch, the first column is missing. For the second branch, the second column is missing. For the third branch, the third column is missing, and so on. Nevertheless, we can still use the rule of product because, and this is important, because the number of ways or the number of arrangements are the same. And because if you go back to the definition, and this is where the definition is important, because it only says that, okay, there are n ways to arrange something else after that. Right? It doesn't say that they have to be the same n ways. They could be different. It doesn't say, okay, the second part needs to be identical for all the cases. No, it doesn't say that. It simply says that if they all have the same number of ways to arrange the second or third or anything. And so this is why we can still use a rule product. Like in this first step, there are 13 ways. And each of these 13 ways, like we have 48 ways for the second step, 48 arrangements. And even though they are all different, like then the number of leaves in each branch is the same. Like the number of leaves in each branch is the same. Even though the leaves are different, but what we care is just a number. So that's why we can still apply the rule product. So now we have to ask, have we finished? We pick 4 cards and then pick the 5th card to fill the hand. And yeah, we do finish. After the whole process, if you pick a leaf, let's say you pick ace and then you pick 2 of a club, then you will get a hand with 8 of heart, 8 of spades, 8 of diamond, ace of club, and 2 of club. Whatever that means. Okay, so that this hand corresponds to this leaf. And you have to stare at it for a moment to see that, oh yeah, we do have all the cases. We are not missing anything out. And that's why we can conclude that, okay, the number of ways we can form this hand is to follow these 2 steps. Pick face values and then pick the 5th card. And by the rule of product, we can conclude that the number of ways we can accomplish that is the product, which is simply 13 times 48. Which I'm not sure what it is. 624. I think, yeah, 624. So of all those cards, there are only 600 ways to get 4 of a kind. And then you can see that, oh, this is kind of rare, I guess. It is difficult to get this hand. And then if you enjoy poker, you see that, oh, this is how they rank the poker hands from lowest, from highest, which is the rarest, the most rare, to the lowest, or the most common. Okay, so that's a rule of product, both in the standard application or in the not standard, but also works here. That's the second part of coding.